Hi, welcome. My name is Ian McGann. I'm a business strategy manager here at Siemens, and I'm going to talk today about accelerated multi-sensor ADAS development with a new data collection solution that we have. To introduce the topic, I'm first going to talk about the levels of automation. So we have level 0, which is no automation at all the way up to level 5, which is a fully automated car. As you go up through those levels, what you're going to see is in level 1 is ACC, AEBS, and then level 2, which is the most common today, is highway pilot systems, traffic jam assist, parking assist. And I also have here sensor fusion. It's important to remember that for later on. Sensor fusion is something that starts with a level 1 and it works its way up and becomes more incorporated as you get into level 5. But we'll come to that a little bit later. In order to help explain the topic of ADAS, we kind of say, well, what is ADAS? And ADAS is an example that we're seeing here where we have a potential collision that is going to happen. A car is driving along at 80 kilometers per hour, and a cyclist pulls out in front of it. And the car now has 29 meters, or 1.3 seconds, in order to stop or make a maneuver. Now, in order for it to stop, there has to be enough distance. And in this case, there isn't. If a car was driving along even at 50 kilometers per hour, it would have 35 meters, and that's on a dry road. So it's not going to have enough time. It really has to make a maneuver. And in this situation, an MPC, or model predictive controller, is typically used to help the vehicle guide around the obstacle, but then also take into account all the boundary constraints. So like the cyclist is moving, so it has to take that into account and its distance. And then you see another very big constraint is the motorbike passing on the left-hand side. So the vehicle has to slow, make a maneuver, pass the cyclist, and then go back into its appropriate lane. So all of this has to happen within before 1.3 seconds, before the potential collision. And the vehicle does that by recognizing its environment around it. It has cameras built into the vehicle. It has potentially radars, LiDARs, ultrasonics, an IMU, a GPS for its positioning, and all of the CAN bus information. And it's receiving all of that information. It's perceiving all of that information. It plans its route, and then it then acts. It does a control. So steers, throttles, brakes, or uses the gears. Now, all of this happens extremely quickly, and MPCs, or model predictive controls, they work like say you're playing chess. They're always looking ahead. They're always thinking ahead, taking new information in and immediately reacting to that information so that they can guide the vehicle around the cyclist safely as possible. Now, if we look at a standard vehicle today on the market, and this is a level 2 vehicle, so if you remember we had 5 levels, so this is a level 2 vehicle. It has a long-range radar, which is in the front. It has a surround camera, also in the front. And if we move around the vehicle, we then get a view of the other types of sensors it has. It has a parking sensor. It has a smart camera up in the dash. It has another nice hidden in the wing mirror, a surround camera. And then the short-range radars are typically hidden in behind the bumpers, and you'll have a few of those around the bumper. And then on the back, you'll have another surround camera, and on the inside is our system that we're going to talk about a bit more, the recorder module and a high-end GPS. And those are the modules that will record all of those sensors and capture all of that information. So at the end, what you're going to see with all of those sensors, you're going to see them all coming in to our recorder unit, and you'll get a view like this. You're going to see the front-facing camera. You're going to see the surround cameras on the left and the right, and we got one on the back as well. You'll also want to see the GPS location. You'll want to see some CAN trace information, and if there's a LiDAR present or a radar present, you might also want to see that information coming through the system as well. This is the objective: is getting this complete picture, this complete recording coming off of the system. But why is ADAS needed? And what we have here is a nice example of a Tesla vehicle that is driving along, and it very nicely avoids a collision. Right? So the Tesla system slows down and stops in time to avoid hitting the red car and avoid this complete accident. And if we take this scenario into account, we analyze it. We use our predictive systems to analyze this. We can see that the radar this Tesla system is analyzing the radar not only of the red car in front of it, but of the blue car in front of that. And it's using the reflections on the ground that are passing underneath the red car, and it detects the blue car is braking and slowing down, and it avoids the accident completely. So why is ADAS testing needed? In this example, we have a bus, and it has a picture of a person on the back of the bus. And the same Tesla vehicle mistakes that person, that picture, for a real person and starts to automatically brake. And we call that a false positive. And that's the type of scenario that we really want to capture. And those scenarios is something that is happening quite frequently as you get into areas of, let's say, unknown testing. So as you start introducing your vehicle into new markets, you're going to see this kind of example more and more. So customers need to test the boundaries of the systems that they've put in place. But the testing isn't easy. There's a lot of different types of cameras. There's a lot of different radars, LiDAR systems, ultrasonics, IMUs, GPS, CAN bus systems available. And they all have these different interfaces. So having a system that is flexible, that can take into account either a GMSL2, an FPD-Link 3 type camera, automotive Ethernet, or standard Ethernet is really important. So you want a system that is going to be extremely flexible. You also need to take into account the bandwidth. Right. As you progress, in the level 2 example we showed was a generation 2, generation 3 type cameras. And as we progress into level 3, 4, and 5, the types of cameras and the bandwidth they produce is going up. So the number of cameras also increases. And this adds a level of scalability to the overall challenge that you have. And to think about that a little bit, we have an example where we're talking about terabytes are generated per vehicle. And the example we have is we have one camera. It's a full HD RAW, 12 to 40 frames per second. So it's 120 approximately megabits per second. We have a radar, which produces about 220 megabits per second. And just a simple example of taking 6 cameras and 6 radars, the complete vehicle can produce 2.040 megabits per second. That's equivalent on a full day of testing, 8 hours, that's equivalent to 58 terabytes. That's an enormous amount of information per vehicle. Now, in this kind of setup, you're probably going to see that more in a level 4 or level 5 kind of setup. So level 2 today is a little bit easier to capture, but you do need a system that can take that kind of bandwidth and scalability. So the system also needs to be able to be ruggedized, right? If you've been in a car, the systems that we typically use here are put in the trunk or the boot, depending on which part of the world you're in right now. So the system needs to be ruggedized. It needs to be able to handle a lot of different operating temperatures from minus 25 to 70 degrees Celsius is what we support. It also needs to potentially have some smart power up, right? If you have somebody driving the vehicle for you, you just want the system to boot up, log in, start recording immediately. So that's an option that we also support. And then you also maybe want to have a smart power down. So we have a optional UPS system that can crank down and shut the system down nice and safely for you. All of this needs to be scalable. So in the example we see here, we have 4 cameras, we have some radar systems, we have our recorder unit, and I'll explain a little bit about more of those little other black boxes. They're called MDIs. And we have a GNSS and a LiDAR. But scalability, well, the cameras and the number of radars can all increase, right? And again, you maybe want to double that again. And we have an ECU in this case, right? So this system needs to be scalable. And that's exactly what our system is doing here, is that you can link multiple systems together, scale the overall setup, and go up to 128 megabits per second. In the end, as I showed before, the result you want is this kind of result, where we have our front-facing cameras, we have our surround cameras, all coming together. So what is our solution? It's a SimCenter Scatter, and it's made up of 3 parts: a recorder, an analyzer, and a replay solution. And I'm going to talk about that in terms of a process flow. So what we have here is typically you would have a test drive. ingestion, you then go into the data visualization, you then have some replay, validation, and afterwards you're going to deploy, and this is at the, say, in the development stage or in the final validation phase. You do some fleet monitoring, and then you come back in with all of your data that you've collected, and you go out and you collect some more. And this whole process is something that we're covering today with our SimCenter Scapter solution. Now, there are parts of this where you have to create your MPCs, you have to analyze your data. That's all in between, let's say. And we've talked a little bit about the perception, the path, and the control earlier on in the session. Our solution, the acquisition system, is a modular system. So it's made up of a storage module, which goes up to 32 terabytes. We have then a recorder, which has some nice interfaces in there for 1 gigabit and 10 gigabit Ethernet, and also your standard USB ports, etc. And then we have these modular ports that you can connect with a CAN FD or a 1 gigabit Ethernet. We also have a very important point here in terms of the raw cameras. So when you're bringing raw cameras in, these are typically serialized interfaces. And what's really important is to timestamp that information accurately. So we have a process where we deserialize each packet, we timestamp, we then do a cycle redundancy check, and then we package that together in a UDP, and we export that out via a 10 gigabit Ethernet connection. So the overall, the data that you're getting, the quality of the data is accurately timestamped throughout the entire process. The nice thing about these MDIs, the modular data interface links, is that you can get them as close as possible to the ADAS ECU as required. Now, this is important because when you're timestamping, you want to timestamp the information as it enters the ADAS ECU. There might be some delay there, and you want to understand exactly what that delay is. Overall, the system, it has extremely flexible interfaces, from the different types of cameras that we can support, going into 10 gigabit Ethernet, the 1 gigabit Ethernet connections, taking into account your LiDAR, your raw radar, your CAN FD, and then the 1 gigabit Ethernet extension cards. The system has the extremely accurate timestamping. This is a GP2P protocol that we're following. And then the synchronization, well, we've talked a little bit about this earlier on. It's got the scalability. So you can add on more modules and increase the overall throughput through our scalable interface. The data cycle for all of this is important to understand as well. So after you've gone out and you've done your test drive, the most important thing is to get the data to the people that need it as fast as possible, which means you don't want to be taking up the time of the vehicle and the recorder. So what we have available is a copy station. So you take your smart storage cartridge out, you slot it into the copy station, and the copy station smartly transfers that over to an on-premise or private cloud solution. And from there, you can start doing your data labeling, your algorithm training, your MPC development, and your system validation. Now, this was all made possible with a company called B+. It's our partner, and I'm going to hand it over to Mr. Alexander Nowak, who's now going to tell us a little bit more about what they do.
Well, thank you very much, Ian, for the short introduction. Welcome to our premises here at B+. My name is Alexander Nowak. I'm the head of the Product Center Automotive Electronics, and I would briefly just like to introduce B+ to you with the experience we have from various projects, with the expertise we put into our products, which you can see in the back of myself. And I would like to just explain a little bit how we started to work in this area. We mainly work a lot along the autonomous drive development, starting at driver assistance solutions 20 years back in time. So 20 years ago, we started to develop the first camera systems together with our customer in the tier 1 area, with a global customer over there. And we worked a lot in the software development at that time. The software development was mainly focused on ECU series software development. So to embed the algorithm, the functionality of the device into software somewhere. In the course of these developments, we started to also see a lot of test and validation system needs at that time. So we started to design test systems. We started to design test adapters. And one of them is shown over here. That's a automotive Ethernet development tool which makes it easy to really address the specific world of automotive Ethernet, for instance. In the course of these developments, there are a lot of tools arised at that time, and also a lot of custom-specific solutions. So we built up systems for test drives. We built up systems for data recording inside the test vehicles. And about 10 years ago, we started to design our own kind of portfolio out of these kind of projects. So until that time, we designed custom-specific solutions, mainly for the sake of this specific customer, this specific use case. We designed it, we produced it, we shipped it out into the world, and we supported that. These systems basically were in numbers like hundreds or even 1,000 units out there. When we started to convert that experience into products like 10 years ago, we set up systems which are helping our customer to design his specific ECU or his specific solution. For instance, one of these devices over here was at the very first time designed for the test of various images for the next generation of camera. So this is why we've designed these kind of interface units just for the sake of this specific process. Nowadays, we use these kind of technologies for converting the high bandwidth raw data interface coming from sensors. Usually it's a SerDes interface, serializer, deserializer interface, which we convert into standard gigabit Ethernet or 10 gigabit Ethernet streams. Why do we do that? Basically, we do that because in the car, the complexity of network is pretty hard. So this is why we use standard technology like Ethernet technology. With this in mind, we can combine things like that together with recorders focusing on Ethernet technology as we see it over here. And this is basically the products we have launched 5 years ago out of these kind of requirements, having a very robust, very high bandwidth recording system for the in-vehicle use, for the sake of data capturing, for the sake of validation, verification, for testing algorithms in the field, in the test vehicle, and for giving purpose to the designer to really test his algorithm at the end of the day. So data capturing over here happens onto specific kind of storage solutions. So this is basically state of the art today. In the future, once we look into topics like data-driven development, we look into much, much more data. We look into terabytes per day per vehicle. And this is why we brought data center technology into the vehicle as well as a next step for the future, which is shown over here. So basically we have a data center, a data lake inside the vehicle, which makes it easy to take data out of the car into the data center, into the colocation space of the data center provider, and to really bring data to the point where it can be used for artificial intelligence training today, for designing new algorithms, for designing new functionality, and for doing tests at hill benches at the end of the day. And this is why we have set up this kind of tool chain, which you can see over here, and brought it into a wider field of standard products, which can be addressed into various projects due to its modularity, long-term availability, and also the reliability of the systems. While we have that in place, we covered a lot of projects at the tier 1 and OEM level for the last 10 years with these kind of standard products. Well, today we join forces with partners like Siemens to widen our addressable market in the field, to really approach other international areas, to use our joint forces to really bring solutions to the customer, and also to combine technology, the technology of the vehicle together with the technology inside the data center, in tools, in software, in services, to really widen the whole range of development cycles. So with this, we basically try to share expertise and share also knowledge about different scenarios. Well, and basically put on that, with these partners, we really can address a wider range of customers and cover a wider solution. Well, and this way I would like to hand back to Ian for these next topics. Thank you very much. Thanks for being here, and thanks for being part of that.
Thank you, Alex. That was a great overview. Really appreciate it. What I want to do now is kind of introduce, well, what happens after you have collected all this raw data and you have trained your MPCs, you then need to do some testing. And what we have here is a nice example of an obstacle avoidance with a real target, where we have a vehicle, again, driving along at 80 kilometers per hour. It approaches the obstacle, makes a lane change maneuver, and then comes back in. Now, the technology that we have been working on is a combination of our simulation and our testing solutions. And we have a very cool software called SimCenter Prescan, which I can inject into the vehicle as a virtual target. I can trick the vehicle into thinking there is a virtual car or a virtual cyclist, and have it make that emergency lane change maneuver. Now, for testing, this is a great way to test efficiently and accurately. Looking a little bit closer at the Prescan solution and our SimCenter Scapter, our SimCenter Scapter goes out and captures all of the raw camera, radar, LiDAR data that you need. We can then convert that into a virtual environment, and we do that in 2 steps. We first have a static environment where we have the roads, etc., and then we have the dynamic environment, which will be the people. And in this case, we're looking at a very cool rally car simulation with SimCenter Prescan and the reel on the right, where the vehicle is driving along, and we have added additional spectators for the purpose of improving spectator safety. This is all done in terms of to train the algorithms and train your MPCs to accurately brake, avoid maneuvers, etc. So I've shown a lot of interesting information related to our SimCenter Scapter solution, to our SimCenter Prescan. Below, you're going to find a lot of useful links, and there are some great upcoming webinars. Please register for them. Thank you very much.